All right, guys, welcome back. We're going to look at section 7.2. So this will be where we actually test our hypothesis, okay? So let's say, we've made some hypothesis about what the true population mean is. We go out and collect a sample, and we have that sample statistic. So depending on how far away that sample statistic is from our hypothesized mean, that will determine whether we reject the null hypothesis or whether we, the way it's phrased is fail to reject it, okay? All right, so in 7.1, we got an introduction or some familiarity with what a null and alternative hypothesis is. Also, what a p-value is, what alpha is, or the level of significance, okay? So we'll see all of that stuff again today. So let's look at these learning objectives. So we're going to learn how to find and interpret p-values. So a p-value, guys, remember, it's the probability of committing a type 1 error. Okay, that was something else that we talked about, the difference between a type 1 and a type 2 error. How to use p-values for what's called a z-test for a mean, okay, whenever the standard deviation of the population is known. And this is always going to be the case in this particular section, okay. Now, in the real world, that's not the case. Okay, so these are kind of simplified problems. How to find critical values in rejection regions under the standard normal distribution, and then how to use these rejection regions for a z-test. Okay, so essentially what we'll be doing here, guys, what a rejection region is, it's an area under the standard normal curve that's so far away from the mean that if your standardized test statistic lands in that area, you say, well, then my assumption that the null hypothesis is true is probably false, okay? All right, so I mentioned this earlier in 7.1, but in a hypothesis test, the p-value is the probability of getting a sample statistic with a value as extreme or more extreme, okay, than the one determined from the sample data, if the null hypothesis is correct, okay. I'll draw some figures here in a minute. It says once we've determined our p-value, we compare it to the level of significance to make our decision. And if you guys remember, if our p-value is less than or equal to alpha, then we reject the null hypothesis, okay? Now, if the p-value is not greater than or equal to alpha, in other words, if it's larger than alpha, then we fail to reject. So the p-value is going to be the area under the curve, depending on the type of test that we perform associated with our test statistic, okay? All right, and then like I said, if our p-value is less than or equal to alpha, then we reject the null hypothesis. In other words, we're rejecting that our initial assumption is false, okay? That the mean is not actually what we hypothesized, and that it's probably some other value, probably a value closer to our actual sample statistic. And then if p is greater than alpha, then we fail to reject the null hypothesis. And in a sense here, guys, this means we're accepting our null hypothesis. All right, well, let's look at example 1. So it says the p-value for a hypothesis test is shown. So this is the p-value right here. These are always going to be given in decimals. This is about 7.15%, okay? And it says use this p-value to decide whether to reject the null hypothesis when the level of significance is these three different values, okay? So there's three parts to this question. So when the level of significance is 0.01, then we are going to fail to reject, because if we compare our p-value, which is 0.0715, if we compare that to alpha, which is 0.01, then the p-value is greater than alpha in this case, okay? So we would say we would fail to reject H naught, or our null hypothesis. In other words, really what we're doing here, guys, is we're saying, okay, well, that test statistic, or that statistic from our sample, is not far enough away from our hypothesized mean, okay, for us to reject the hypothesized mean. All right, now what about part B? Well, here, if alpha is 0.05, then we're still going to fail to reject, because our p-value is still greater than alpha, okay? Still fail to reject H naught, or null hypothesis. Now for part C, our p-value being 7.15% will actually be less than or equal to alpha, which in this case is 10%, okay? So in this case, we would reject H naught, or the null hypothesis. But I'm going to tell you guys, if you were to look at any sort of statistical studies, alpha of 10%, that's not a very strong value for alpha. Typically, 0.05 or 0.01, these are the most commonly used values. So if you end up rejecting H naught under this level of significance, 0.01, that's a pretty strong test. And then even this one is a fairly strong test, okay? But what you're saying here is that there's a 5%, if you reject your null hypothesis, there's a 5% chance that you're wrong, essentially. And you'll be wrong, okay? All right, so let's look at how we actually find the p-value. Okay. Well, after determining the hypothesis test's standardized test statistic, okay, you're going to do you're going to find the p-value for a left tail test. Is going to be the area in the left part of the tail. Okay, so you're gonna find X bar, that comes from your sample, and then you're going to standardize it. And then you're going to look and see where that z-score lies. And if it's a left-tailed test, the p-value is going to be the area to the left of that z-score. Okay, like in this example right here. If it's a right-tailed test, it's going to be the area to the right, okay, of that test statistic. Now, sometimes you'll be performing a right-tailed test, guys, and the actual statistic from your sample can still end up being on the left, in the left tail. That occurs sometimes. And then for a two-tailed test, you'd find your test statistic. Okay, it's either going to be in the left or in the right part of the tail, and you're going to figure out what the area either to the left or to the right of that tail is and double it. Okay, because for a two-tailed test, you're counting the area that's in both tails, essentially. All right, so let's get some practice doing this, because this is how to find our p-value. And once we know that p-value, then we can actually reject our null hypothesis or fail to reject it. Okay. All right, so find the p-value for a left-tailed hypothesis test with a test statistic of z equals negative 2.23. Okay, so let's pretend that we had some hypothesized mean, and so if we standardized it, it would be 0. And we take a sample, we get that sample mean, and we standardize it, and it's negative 2.23. Okay, so it's way over here. So if we're performing a left-tailed test, then essentially what we're doing is trying to figure out, well, how much area is to the left of this z-score, okay? All right, so if you recall, guys, you can use a table, you can use Excel. I showed you all of those things. You can also use our calculator. If you come over here to distributions, and it's going to be in the normal CDF, okay? Remember, what this gives you is the cumulative area under the standard, well, under any normal distribution, but you have to specify what the mean and standard deviation are. Whoops. Let me try this again. Here we go. Okay, so you want your lower bound to be, remember we were referring to this as negative infinity, even though it's not technically negative infinity, because so far to the left of the mean it might as well be. So if this is our lower bound, then our upper bound would be our z-score, or our test statistic, negative 2.23. And then we're going to be using the standard normal distribution, okay? So our mean is going to be 0, and then our standard deviation is going to be 1. Oops. And if you look in here, well, let me write this out. P, so this is, again, this is the area to the left, okay? So we've done this before. You guys know how to do this. It's equal to, if I round this to 4 decimal places, the way it's been done in this figure, this would be 0.0129, okay? So this is our p-value. In other words, this is the probability that if the mean is what I hypothesized, the probability of taking another sample and getting a test statistic that's even farther to the left, okay? Because that's the area under this curve. So that's really what you're finding. All right, well, to actually determine whether we reject H naught or not, we look at alpha. We compare this p-value with alpha, okay? Well, 0.0129 is actually larger than 0.01, guys, okay? So in this case, because p is greater than alpha, then we fail to reject, okay? Reject H naught. In other words, essentially what we're saying here is that, we're real close to rejecting it, but it's not quite. So what we're saying is that whatever that test statistic was, it's not far enough away from the mean for us to assume that our initial assumption was incorrect, okay? If it were just a little bit further to the left here, then we would reject the null hypothesis and in favor of saying, well, probably the mean is not what I hypothesized it to be. Okay. All right, well, let's look at part C. I've got one of each in which we use each type of test, okay? So we just looked at a left tail test. So now part 3, or example 3 here, it says find the p-value for the indicated hypothesis test with the given standardized test statistic. And then decide whether to reject H naught for the given level of significance. All right, so here we're going to be performing a right tail test, and this is our test statistic, okay? It's 1.24. Now, like I said, because sometimes I've seen this in students' projects before, just because you be performing a right-tailed test doesn't necessitate that your test statistic has to be negative, or excuse me, positive rather. Sometimes it ends up being negative, but anyway, and then alpha is 0.1, okay, so 10% in other words. All right, well, if we're performing a right-tailed test, I'm going to go ahead and draw a standard normal curve for us, okay? So we're hypothesizing that the mean, the true mean, is right here. And we take a sample and we get a sample mean that when we standardize it is 1.24, or in other words, it's 1.24 standard deviations away from this hypothesized mean. Okay. Rewrite this as z. Okay. All right. So to be performing a right tail test, what I need to do now is figure out how much area is in this right tail, or in other words, figure out how much area is to the left and subtract that from 1. Okay. So if you guys remember, well, that's what we don't have to do it that way. If you're using your calculator, remember what you can do is you could try to figure out, well, how much area is there under this curve from negative infinity all the way up to 1.24 and subtract that from 1. And that'll tell you how much is here in this tail. Okay. But the calculator, you can actually let the lower bound be the test statistic and let the upper bound be positive infinity. I think this is the way I explained it, or did it most often in class. Okay, so that's what I'll do again. So I'll let my lower bound be 1.24, and then I'll put in here 1. Remember, you need to put in a capital E and then raise it to the 99th power. And then, of course, our mean and standard deviation are going to be the same. If I hit enter, this gives us the area to the right of the curve. Okay. All right, so this area right here, P, is equal to 0.1. Let me round this to 4 decimal places. 1075. Okay. All right, well, what we need to do now is compare this with alpha. Well, again, coincidentally, this value is greater than alpha. Okay, alpha is like 10%, and this is like 10.75%. Okay, so P is greater than alpha, and so we fail to reject H naught again. In other words, we would like for this test statistic to have been a little further to the right before we would actually reject H naught, okay, or our null hypothesis, given this level of significance. All right, let's try example 4. So here we're going to be performing a two-tailed test. It says find the p-value for the indicated hypothesis. Okay. Well, I'll go ahead and read it. Hypothesis test with the given standardized test statistic, Z, and then decide whether to reject H naught for the given level of significance. Okay. Well, we'll be performing a two-tailed test, so what we're trying to do is figure out how much area is in both of these tails. Now look, our test statistic comes up positive, and when you're performing a two-tailed test, your test statistic can just as likely come up positive as negative. Because essentially what you're testing here is, what your null hypothesis is that the mean is just not equal to some value. You're not saying that it's greater than or equal to some value. There's just not equal to some value. So if that's true, and you take a sample, then that sample statistic could just as easily fall underneath or below your hypothesized mean as it could fall above your hypothesized mean. Okay. Well, in this case, it falls above. It's 2.14. And guys, this is actually pretty far from the mean. 2.14. So what we need to do here is figure out how much area would be in this tail and then double it. Okay. Because this corresponding negative z-score would be negative 2.14. So we're trying to figure out what's in both of these tails. So we could use our normal CDF again. And I'll let my lower bound be 2.14. And I'll let my upper bound be positive infinity. We'll see how much area. Okay, so this is what I get. So since I've got this number stored in the memory of my calculator, I'm going to go ahead and double it. Okay, it'll save me an operation. All right, so I get a total value for P, the total area in both tails of P is equal to, I could just copy it from the figure, 0.324. Whoops. 0.0324. Here we go. Okay. All right, so now to determine whether we essentially keep or reject our null hypothesis, we need to compare this with alpha. Now, alpha in this case is 5%. And this test statistic is less than, or excuse me, this p-value is less than alpha in this case. So, because of that, guys, we will reject our null hypothesis. In other words, that test statistic, when standardized, is far enough away from the mean that we can say that if the hypothesized mean is correct, the likelihood of me getting a sample statistic that far away from the mean is only 3.24%. Okay? That far or farther from the mean. All right. And let's continue. So we haven't really talked about this, although we did work with this when we were calculating the margin of error. You may be wondering, well, how did you find the z-score? Okay, because it was given to us in these. Well, we don't actually know what the average of the raw distribution or the sample was. It didn't tell us. It just gave us the standardized score. Okay, so the way you standardize it, guys, is we've done this before. Is you take whatever your sample mean is and you subtract from that the hypothesized mean, and then you divide it by the standard deviation of the population over the square root of n. So remember, we're talking about a distribution of sample means, and that distribution of sample means is actually much tighter than the original distribution would be. Okay, so that's what this square root of n does, is it makes the variance of this distribution of sample means much tighter. Okay. All right, so when sigma is known, we can use what we call a z-test to make decisions about a claim regarding the mean. Okay. So to use the z-test, you got to find your standardized test statistic. Now, before that was given to us. By the way, guys, we were actually performing a z-test down here. Okay, we were deciding whether to reject or fail to reject the null hypothesis. Okay. So this is the formula that we use. Mu is the hypothesized mean given by the null hypothesis. Okay. And then once we have that z-score, we use that to find the p-value, because once we know the p-value, we can compare that with alpha, our level of significance, and that will dictate what we do. Okay. And this just kind of summarizes everything that we've discussed. Okay, so let's try one of these. It says a random sample of 89 8th grade students' scores on a National Mathematics Assessment test has a mean score of 273. This test result prompts a state school administrator to declare that the mean score for the state's 8th graders on this exam is more than 270. Okay? Because the actual mean from the sample is larger than 270. Okay? So assume that the population standard deviation is 33, and then at a level of significance of 6%, is there enough evidence to support the administrator's claim? All right, guys, so what I like to do first, what we need to do is first go ahead and state what our null and alternative hypothesis is. Okay, so look here. The administrator's claim is that the mean score is more than 270. Okay, so that doesn't have an equality component in it. So that his actual claim is going to be our alternative hypothesis, that the mean is strictly greater than 270, which means our null hypothesis is that the true mean is less than or equal to 270. Okay, and I'm going to denote right here that this is the claim. The claim of the school superintendent administrator is being represented here by the alternative hypothesis. All right, so go ahead and do this first. Now I'm going to find our standardized test statistic, and then we'll find P, and we'll compare that to alpha, and that'll dictate what we do here. All right, well, let's go ahead and define N as 89, okay, because we're going to be using that formula. It's x bar minus the hypothesized mean divided by standard deviation over the square root of n. Okay. X bar is right here. It's 273. And then the hypothesized mean is 270. And then the standard deviation sigma is 33. Okay, so let's plug these values in. Be 273 minus the hypothesized mean, which is 270. And then we'll divide this by 33 over the square root of 89. So you can plug all this into your calculator. Well, I'm going to keep that numerator. Well, guys, 273 divided by 270 is just 3. So I could just say 3 divided by, and then I'll keep my denominator in parentheses, 33 over the square root of 89. Oops. Well, I needed to get out from underneath that radical first and then close my parentheses. Okay. All right. So let's hit enter. Okay. So we get a standardized test statistic. It's kind of a tongue twister, by the way. Is equal to 0.85776. Okay. So this is our value for z. Well, this is positive, okay, but we're going to see if under the standard normal distribution, this is far enough away from the mean that we can actually reject the null hypothesis. Okay, so let's draw a little picture here. A little standard normal distribution. Okay, so our hypothesized mean of 270, if we standardized it, it would be 0. Okay, and then our test statistic comes up 0.8576. Okay. And remember, the type of test that you're going to be performing is dictated by the alternative hypothesis. So if this says greater than, we're performing a right-tailed test. And if you remember that trick that I told you, the direction in which this inequality symbol is pointing, that's pointing to the type of tail test you use. So it's pointing to the right. Okay, so we're going to be performing a right-tailed test. In other words, we're trying to see if this test statistic is far enough away from this hypothesized mean that we could reject the hypothesis. Now, rejecting the hypothesis would actually favor the superintendent's claim. Because, see, look what we're hypothesizing, guys. We're hypothesizing that the true mean is either 270 or less. Okay, so if this claim is true, we would expect to get a standardized test statistic maybe somewhere up to the left. Okay, all right, well, let's find the area to the right here. All right, so I will use my normal CDF function again. my upper bound, move this up, 0.8576, and then my upper bound will be positive infinity. Enter. Alright, so, okay, this is a fair amount of area, okay, and I figured it would be because, you know, this is not even one standardized or one standard deviation away from the mean, this particular value. All right, but nonetheless, this is our p-score, and it is equal to 0.1956. Okay. Well, now we're going to compare our p-value with our level of significance alpha. So our p-value is 0.1956. Guys, that's actually greater than alpha because alpha is only 6%. So p is greater than alpha. So when p is greater than alpha, we fail to reject, okay, H naught. So when we fail to reject H naught, that's sort of like we're accepting it. And we're going to continue to assume that the mean is 270 or less. Okay, so that would actually contradict what the school administrator claims, because he or she's claiming that the average is actually greater than 270. Well, in order for us to reject the null hypothesis, we would have needed an actual sample average to have been quite a bit greater than 270. So if this had been like, you know, 300 or 350, then we probably would have rejected the null hypothesis in favor of the administrator's claim. So try to kind of put that in the context of the problem for you. All right. I also want to show you, using the calculator, that you can perform a z-test in the calculator, guys. If you come over here to Stat and go over to Tests, it's this very first one. If you hit Enter, you're either prompted to actually input the actual data from the sample or use the statistics from the sample. So if I hit Enter for statistics, I would actually put in, you know, this is what you would put in for the hypothesized mean. So I put in here 270, and then the standard deviation of the population that is given to us, it's 33, and then the mean of the sample, or x bar, is 273, and then the sample size, n, is 89. And then you just come down here and you select the type of test, okay? So you basically look at your alternative hypothesis. So this says greater than, this is a right tail test, so I'm going to click Enter, okay, for this one. And then you can come down here and you can just hit Calculate. And what it will do is, it not only calculates, it standardizes your test statistic, okay, it'll give you the p-value. And with the p-value, you can then compare that to alpha and figure out how to, whether to reject or fail to reject your null hypothesis. Okay. Let me go back to that real quick because I want to show you. It will also draw you. You can redo it or just run it again. You can come down here to where it says Draw, and it'll sketch the standard normal distribution. Well, I've got a function in here. That's why I was sketching that other thing. Let me quit that. We go to Zoom and then Stat, and we'll see it again. Well, I thought we would. Well, let me just try this again. Come down here to draw. Yeah, there it goes. So see, it shades in the area to the right of that standardized test statistic. And so because this is a lot of area, we don't reject the null hypothesis here. So anyway, guys, make use of that if you need to. Okay, I could have done those others using this z-test function as well. Yeah, I could have done those others using the z-test function as well, right? Because they're looking for the p-value, or the probability. So, and I'll try to show you that again as well. Okay, that's number 5. All right. Yeah, well, yeah, let's, I was trying to think if I want to break this up into 2 different videos. Really, all we're doing here is just more of the same. We're just looking at it from a different perspective, that's all. And I think I will break this up into 2 videos, guys. What we'll be doing in the next segment is we'll be we'll be looking at alpha, and depending on if it's a left-tailed, right-tailed, or two-tailed test, we figure out what z-scores would be associated with alpha, okay? And then if our test statistic falls in that area is called a rejection region. If it falls in that area, such that, for example, 5% is in the right tail. Well, if our test statistic falls in that rejection region, then we reject the null hypothesis, okay? But I'll save that for the part 2 for this one, because this material is kind of dense.